So I'm going to talk about a particular type of algorithm, which is called stacked ensembles or stacking. There's a bunch of different names for it, which I'll talk about because sometimes you learn about something in data science or machine learning, and then you realize it has another name, and then you think you know two different things, but then they're the same thing. So it's always good to know if there's multiple names for something. So I'll go over that. And then all right, so this is the agenda of the talk. So I'm going to just say a little bit about who H2O is and then what is H2O, the software. I'm going to talk about what is ensemble learning, and then stacking, another name for it is super learning. That's a particular type of ensemble learning, and I'm going to tell you like how that's different from other types of ensemble learning. Then I'm going to give you some motivation for like, why would you do this? Why is it better than other algorithms? When is it not as good as other algorithms? Sort of the pros and cons of stacking. And then compare it to grid search and talk about stacking with other algorithms outside of H2O. Because the main software that I'm going to present is stacking for H2O, so it's within the H2O software itself. And then I'm going to sort of introduce a concept that's called AutoML or automatic machine learning, and talk a little bit about what we're doing with AutoML and stacking. All right, so how many of you have heard of H2O before coming here tonight? Okay, so only like half. Okay, so we're a company in Mountain View. And we've been around since 2012, and basically the company was formed to be a company that produces open source machine learning software for big data. So I don't know, sometimes like an open source project is around for a while and then maybe a company spins off from it or something like that. But the whole point of H2O from the beginning was just to make a company that had that produced open source software for big data. So there's a lot of libraries that do machine learning that are very popular, like scikit-learn, or in R there's like the Caret package, which is sort of a meta package on top of a whole bunch of other packages. But one of the issues with some of those packages is that they weren't, I guess when they were first written, not designed for very, very big data. So they're harder to scale. You have to do a lot of manual work to actually get them to scale. And so the whole point of H2O was to build an open source machine learning library that actually was built in a way that was meant for big data from the beginning. And the way that we write all the algorithms is distributed. So you can run them on a single laptop or a single machine, but they're really meant to be run in a distributed fashion. And you actually have to write the algorithms differently, and that's why it's kind of hard to take an algorithm like scikit-learn and then turn it into a big data library after the fact. So it's open source software, and it's written in Java, but we have APIs in R, Python, and Scala, and a web interface as well. So it doesn't matter which language you like to use. So that's kind of the idea. And then if you're into machine learning at all, you might recognize a few of these people, at least maybe the first two. So Trevor Hasty and Rob Tibshirani are professors at Stanford that have a book that's pretty popular called The Elements of Statistical Learning. So if you're coming at machine learning from maybe a statistical background, you'd probably definitely know who these people are, but they're statisticians and computer scientists. They kind of like live in two different worlds sometimes. So maybe if you're coming from CS or some other world, you might not know who they are, but they've invented a lot of the algorithms that you would recognize, like gradient boosting machine, GBM, the lasso regression method, etc. So anyway, the reason I have them up here is they are our scientific advisors at H2O. Okay, and so this is actually going to be the most complicated slide that I show you tonight. So this is just a little bit about like how we do distributed computing at H2O. So there's two concepts that you should maybe know about. You don't really need to understand this, but I think if you're interested in how we're actually doing the distributed computing, this is helpful. So there's two things. One, something we call the H2O cluster, and this is just the name for basically a Java process that's running on a bunch of machines, where all of the machine learning and all of the stuff in H2O happens. So you can run a cluster on a laptop and it would just be like a little mini local cluster, or you can run it on like EC2 and actually have like a physical big multi-node cluster. And so that's what we just call the H2O cluster. So all the computation happens in there. And then the other concept is something that we call the H2O frame. And so this is how all of our distributed algorithms work, and how they are distributed is because unlike like in R or Python where you have a data frame which is just sitting in memory on a single machine, this is a data frame that kind of looks like it's sitting on your machine, but it's actually split up over a whole bunch of machines. So when the algorithms in H2O work, the way that they work is, some subset of the rows are on this machine, some subset of the rows are on this one, and this one, and this one. And what they do is they sort of operate on the local data and then make, sort of informational updates to each other about what's going on the other nodes, and then sort of exchange information. So there's basically a lot of communication happening between the nodes. So those are just some concepts that if you're interested in the distributed computing are good to know about. But when you're using H2O, you see like an H2O frame just like a pandas data frame or an R data frame. You don't know that it's on a bunch of machines, and you don't have to know that. Okay, so that's the most technical thing I think that I'll share. So now I'm just going to talk about what is stacking. Okay, so stacking is a form of ensemble learning, and if you haven't heard of what ensemble learning is, it's basically taking a bunch of different algorithms and combining them together into like a single algorithm that takes input from all the constituent algorithms. And then the idea behind that is that you can get a better performing algorithm by taking the input from all these different algorithms, because maybe some of them have better performance than others on certain types of data. So you're just kind of like taking the I don't want to say taking like the average, because that's actually not what stacking is, but I'll explain how you combine those things together. Okay, so if you have heard of ensemble methods before, you're probably more familiar with bagging or boosting. So how many of you have heard of random forest before? Okay, so like pretty much everybody. So that's a type of bagging. So bagging basically just means you're averaging a whole bunch of things together. And with random forest, you average the decision over a bunch of trees, and the trees are randomly created. That's why it's called random forest. So that's an example of bagging. Boosting is a little bit different. It's more of like an iterative algorithm. So random forest is very easy to do it all at once. You just, if you wanted to parallelize it, you could just say each node do one tree or something like that, and then average them together. Boosting is an iterative algorithm by nature. So that means that you do sort of one iteration, and then based on the results of that, then you do another one, and it like learns from the mistakes of the past iterations, sort of, is one way to think about it. And I'm not going to necessarily explain boosting, but so there's, I guess my point in this slide is maybe just pointing out some of the pros and cons, or some of the features of these different techniques. So boosting is, both bagging and boosting are good for reducing the variance, which just means, is another way of saying it increases the accuracy of the final model. One thing that's a little bit weird about boosting compared to bagging is that if you have outliers, sometimes that can affect your boosted algorithm a little bit more than bagging. So because the way boosting works is paying attention to the ways that the algorithm got something wrong, if you pay too much attention to the outliers, like doing a bad job, then you can kind of overfit. So boosting in general is I mean, if I used to use random forest a lot, and these days I use GBM a lot. GBM, gradient boosting machine, is a um, type of boosting method. And so I would say, like, in general, GBM is probably better than random forest, but you have to be a little bit more careful about tuning and that type of thing. So random forest may be easier to use, but GBM, typically you can get a little bit better performance. Let's see. Another nice thing about boosting is that you can tell it to pay attention to any sort of loss function that you care about, if that's of interest to you. Okay, so those are the two common types of ensemble methods. And so a lot of times I see like blog posts about, like, you know, ensemble learning, and they just like completely ignore stacking, and it makes me so sad. But so bagging and boosting are, you know, kind of the more popular ones. But stacking is actually you know, the best performing out of all of these typically. So the thing about stacking that's a little bit different than these other two is, one is typically you use a diverse set of learners. So with both bagging and boosting and the examples I gave, like random forest and GBM, you use decision trees typically as the base learners in your ensemble. But there's no like other algorithms going on there. It's just decision trees. So with stacking, you would maybe use, like, you could even use a random forest, a GBM, an SVM, a deep neural net, and you take all of these very diverse algorithms and you combine them together. So one thing to note is that you know, you're typically dealing with different types of base learners. And then the second part is that you actually use machine learning to learn what the best combination of those algorithms is. So there's actually two stages of machine learning with stacking. One to train all the base learners, and then another to learn what the best combination of those learners is. So, and that second step of machine learning is called meta learning. So I said that other slide was the most technical slide. This is the most mathematical slide. Actually, these next two, because I have matrices on there, I guess. So I'm just going to explain what stacking is, because it's actually a very simple algorithm. And if you know how to write some code in Python or R, and you're familiar with some library like scikit-learn, you could actually implement stacking yourself. And a lot of people do that in Kaggle. It's just kind of like a pain to do that. So that's what the software that I'm presenting is all about, is to do all that for you, so you don't have to like write all the code to do all this stuff that I'm about to show you on the next two slides. But it's actually not too difficult. So what you do is you start, this is like your general setup for any machine learning problem. You have your training data here, like let's say there's n rows and then m columns. So that's your training data, and then your response y. So that's every machine learning algorithm, well, I shouldn't say every. So every supervised machine learning algorithm pretty much starts out that way. And then with stacking, you have basically two jobs. One, to decide what learners you want to go into your ensemble. So you have to specify, you know, I want a GBM with this number of trees with this depth and whatever. So like a fully specified model for each of the base learners. And then you specify your meta learning algorithm. So the algorithm that is the one that you use to combine the learners together. And for this, there's kind of like a subset of algorithms that work better than others. So so just to note that. But for base learners, you can basically throw anything in there. And the first step of this whole process is just how many of you are familiar with k-fold cross-validation? Okay, so like most people. So I should probably have a picture of what that looks like. But basically, this would be like a good homework assignment, is like Google k-fold cross-validation. And then you'll know the missing piece of this algorithm. But basically, for each of the algorithms, you just perform k-fold cross-validation on it. And the reason that you do that is because when you do k-fold cross-validation, what you end up with is is basically a column of predicted values. So for each one of your n training observations, you'll get like a cross-validated predicted value. So in the way, I'm not going to really explain what k-fold cross-validation is, but that's sort of like what you end up with. And then usually if you're just using that for model selection, you might then, you know, take this output and find like the, you know, k-fold cross-validated accuracy of your model or something like that. But for now, we're just going to stop with the predictions. So this is where the stacking name comes from. So basically, each of your, in this case, we're going to say we have L learners in our ensemble. So maybe this is an SVM, this is a random forest, this is, you know, whatever, this is a GOM. And we're going to take those predicted values and like stack them together into a new matrix here. And then we're going to do machine learning again. So we have n rows, and L is the number of learners in your ensemble. So it's a different size matrix than you started out with. It's the same number of rows, but it's skinnier. And then you're going to train another machine learning algorithm on this data. So you're going to stick your Y on the end, and then that's the meta learning step, and then you're done. So if you think about what you've done here, basically on the second stage, you have an algorithm that takes the predicted values from the base learners and then combines them together to predict Y. So that's kind of what's going on. So if you were to write this, you know, in some blocks of code, you would say, okay, for the predict function, you would say, okay, tell me from each of the base learners what your predicted value was. Okay, thank you, thank you, thank you. You grab them, and then you give them as input to your meta learner, and then you say, here's the predicted values, and then it spits out the final answer. And that's basically what's going on. And if, you know, and the fortunate thing is you don't actually have to think about this if you use the software. If you write it yourself, you have to do this, but basically that's what's going to happen. But under the hood, you know, there's not that much going on. So one of the things that people say about stacking, I think, that's maybe a little bit unfair is they say it takes so long, you're training all these algorithms, I don't have time for that or whatever. But in fact, typically, like as a data scientist, if you're deciding between a bunch of models and you're trying out an SVM and a random forest and sort of like comparing the results, and then you want to pick one at the end, one of the ways that you could do that is to do cross-validation on each of the algorithms. You could also just use like a test set or a validation set and choose it that way. That would save you time. But if you're going to do cross-validation, you're already doing like 95% of the work of stacking. So, so when people say it takes too long, I just disagree with that, because I think for the most part you're already doing most of the work, and so what's the harm in like just throwing a meta learner on there to see if you can get a little bit better performance? So if your goal is really to get a single algorithm and not an ensemble, then you're probably not interested in stacking. But because sometimes like people choose simple algorithms for whatever reasons, like in production they want it to be the simplest thing, they want it to be a GLM or something like that. But if you actually care about performance, then and you don't care as much about like complexity, then stacking is really the best thing that you can do. So anyway, this is my like motivation to try to get people to see that basically stacking is essentially grid search, but with one little extra step. A cross-validated grid search. Okay. So, so why would anyone want to do this? Well, one answer is that this is the only way to win Kaggle, basically, these days. It's true that sometimes people win without stacking, but for the most part, like, this is how people are winning. And it's like, and this is why, because this is like a ranking of this particular competition where this is number one, number two, whatever. And so these are like the differences that you're dealing with at this level. So we're dealing with like the 4th decimal point. That's how you win Kaggle. So if you need to like squeeze all the prediction power out of your data, stacking is a perfect opportunity to do that. And so when people win on Kaggle, they usually do a little write-up and say, how did they win? And so basically, here's just an explanation of like, this is on this particular competition, this is the #1 person explaining what they did. So they did an ensemble of regression random forest, a classification random forest, a feed-forward neural network, a GBM, a regression GBM, and a classification GBM. And these are all algorithms that we have in H2O, so they very easily could do this in H2O. But I'm sure this person wrote their own code to do it. But yeah, and then this is, I thought was interesting too, is they said one of the things that they thought was useful of their team was that their team was like an ensemble as well. It's like everyone had like certain skill sets, and when you bring everybody together, that like works really well. Okay. And this is just the 2nd place person saying, you know, they had 15 models, you know, GBMs, weighted GBMs, random forest, all these different like variants of different algorithms. So that's what they did. So now I'm going to talk about like H2O and how you ensemble with H2O. So one of the reasons that I started working on H2O. So before I worked at H2O, so I've been there for 2 years. But before I worked there, I was doing my Ph.D. and I was doing research in ensemble methods. And so I needed a package that had a whole bunch of algorithms in it that I could just use to test all my ensemble stuff. So there was basically like scikit-learn would be an example of a package with a bunch of algorithms with kind of like a common interface. The caret package I've mentioned before in R, the MLR package. So basically, I just needed some package that had a whole bunch of algorithms already in there. So this was a good, and actually then there was a couple R packages that I was using. One is called Superlearner, and the other one is called Subsymbol. And those are both packages that I've worked on, but they're not scalable at all. So I would be waiting for like weeks for my ensembles to finish, and it was just really frustrating. And because they all just use like random implementations of algorithms in R that are, you know, probably not super scalable. So, you know, you can only do so much. So I looked to H2O and I saw, okay, these are scalable algorithms. I could write a thing on top of H2O and then it would all just work. So I wrote this package called H2O Ensemble, which is just an R package, which was on top of the H2O R package a couple years ago. And that was fine. Like none of the machine learning was being done in R. It was all being done in Java. I was just sort of telling Java what to do through R. But then that's not typically how we write algorithms in H2O. So usually they're written in Java, and then we can expose them equally to all the different APIs. So it's once they're written in Java and we write all the little endpoints in our REST API, then we just basically, it's very easy to add Python or R or whatever APIs to it. So that was sort of a limitation of this, is like Python people couldn't use it, for example. So we moved all the code into Java, and then sort of re-exposed these methods in H2O R package, H2O Python package, etc. So now this still exists, but this is kind of like, you know, in native H2O now. So this is the one that I'm going to talk about today. And this is new. And so you don't need this extra little add-on package anymore. And if you have Python now, you can do it. Okay. So so one of the things that I kind of find to be annoying about stacking is like you have to come up with a whole big list of like models to put in the stack to begin with. So you know, that's not that hard, but like it's easier if you have some way to do that automatically. So one way that we came up with is if you just do like a big random grid search for each algorithm, then you have kind of like a random assortment of GBMs, a random assortment of random forests, and blah, blah, blah. And then you can just like glob them all together into an ensemble. So, anyway, and so I kind of was like emphasizing like diversity in the ensemble is good. So this is also a good way to get like diverse base learners is if you use random grid search. So I'm just showing you right here in R how to do this is actually not a random grid search, it's like a regular grid search. So this is how you would do deep learning grid search, for example, with these options. So these are just like the number of neurons and number. So this would be a multi-layer perceptron with 2 hidden layers, each of 200 neurons each. This one would be 3 hidden layers. So basically I'm iterating over a few different architectures for the deep neural net. And then this is just the L1 parameter, so just a couple of different values of that. And so this would just take all the different combinations. This is the regular grid search or Cartesian grid search. And this next slide just shows if you want to make this a random grid search, meaning it just randomly samples from that grid for a specified number of time or a specified number of models. Or there's other ways to tell it how to stop that are based on performance. Just add this extra thing here. So this object grid is just going to be like a list of models. And then if you want to stack them together, the stacked ensemble function, which is the new one that I'm talking about today, is just you pass in a list of models. And this is just kind of like an example of, let's just say I trained a random grid of GBMs, a random grid of random forests, etc. Just like put them in a list together. It's actually not a list, but I don't know if that. Actually, each of those are lists, so actually when you take the concatenation, it will be a list. But anyway, so this is basically the interface. You can ignore this for now because this is the only thing I've implemented for that. But yeah, you just give it a list of models, and it will stack them together. This is how you do it in Python. So if you haven't used H2O before, you might, I don't know, the X and Y and training frame notation might be a little bit new to you, but so if you've used scikit-learn, usually X is actually a matrix and Y is a column or something like that. But the way that we do it in H2O is just add some flexibility to sort of separate these two. So you give it your training frame, and then X is just the list of columns that you want to use at that given time. So it just lets you more easily choose different subsets of columns if you separate the columns from the actual thing itself. So in this case, X is not a data frame, it's a list of column names or column indices. And Y would be the response column. Okay, so I'm just going to show you a little demo. How about I could either do it in R or Python. I don't want to think I'm going to run out of time, so I'll just choose one. How many of you would prefer the Python demo? Okay, how about the R demo? Oh, only 2 people for R. Okay, I'll do Python. Okay, so if you click on these links, this will take you places. So this is just how to get to the old, I shouldn't say old, like I'm going to keep maintaining this, but, you know, I guess I would probably recommend using this one if you're just getting started. All right, so what that does is it brings us to the documentation page. And I'm going to show you just a couple things first. One is like, how do you install H2O? So you can just do pip install H2O for Python, and for R, just install packages H2O. So that's pretty easy. And then what else was I going to show you? Oh, how do you get to the docs? So if you go to docs.h2o.ai, oops, too big. This is kind of like the main H2O user guide or documentation. And this is where I would go if you're like new to H2O probably. And then we have some stuff about all of our different algorithms. So this would be under data science algorithms. Here's like all the ones that we have implemented. So Stacked Ensembles is at the end. And this is basically the sort of homepage for the Stacked Ensemble method. It'll tell you like resources and links to things. But mostly why I'm going here is the code. So this is just example code. So one thing that I noticed as I was running this demo before is that there's a few typos in this documentation. So actually what I did was, and I couldn't push the changes because it only goes every night. So unfortunately, there are some typos in here. So what I did was I fixed the typos and I put them as a gist on my GitHub. So if you go, I'll show you how to get there if you're interested. So you just go to github.com/my last name, Ledell. Actually, I should probably just go right to gist, but you can click on that. And you'll see like one of my most recent ones is, this is just that same code, but I fixed the typos. So, so we'll run it from here. And maybe I could, let's see if I can just do this. All right, so what I'm going to do is just open up the window. Let's make it really big. Okay, can everyone see that okay? In the back? Okay. So, all right, so in this little code demo, there's just two different ways to make an ensemble. So one way is just you're training H2O models and then you grab them together in a list and you pass it on. And the other way is when you do a grid search and you use that as your starting point for the ensemble. So all of this code at the top here is just basically importing, here, let me make this bigger too. So just importing everything that you need. And this is starting the H2O cluster. So that's the first step in any time you're using H2O is like starting up the cluster. N threads equals -1 just means use use the same number of threads as the number of cores on your machine, basically. So if I'm running this on my laptop, so this will start like an 8 core cluster, sort of. So let's do that first. So paste that in. Okay, so what it will do first is it'll just check if there's already an H2O cluster running. And I'm not specifying any of the parameters, basically. So typically, if you're running this on AWS, you would put in like an IP address and a port and some other things. But since I'm just running on my laptop, the default is localhost, basically. And actually, I'll show you what it does. So when you start up an H2O cluster, one of the things that it does is start up a local web server. And this is the GUI for H2O. So you can do everything that you can do in H2O from the GUI as well. So if you like GUIs, then this is, a great thing. So here's like all the modeling. Oh, one thing you can't do is do Stacked Ensemble yet. That'll be in the next release. So I lied. But you can see them once they're in there, but yeah, that is coming in the next release. And you can kind of switch back and forth. So sometimes what I do is I train a bunch of models and then I look at them in Flow because it'll automatically do a whole bunch of plots and like things that you would have to like type a lot of stuff to do. So let's go back to Python and look at what happened here. So first it looks to see if there's already an H2O cluster at that particular IP address. And if not, it says like checking whether there is one running. Oh, I didn't find one, so now it's going to start up an H2O cluster. And then it just prints out some metadata like about the cluster. So what version of H2O am I using? This version is 5 days old. There's one node, which means one machine. By default, it will give you 4 gigs, but you can tell it however much memory you want, like assuming you have that much memory on your machine. So this is just a tiny example, so that's more than enough memory. And then the number of cores is 8, so that's the number of cores I have on my laptop. And I guess, you know, for Python, they'll say which version of Python I'm using. Anyway, so just some metadata. And then, where were we? Oh yeah, we were going to use the one from gist. Okay, so this is just how you import files. So import file is a pretty generic method. So you can give it like a URL. You can't see that, I guess. But this is a URL of a CSV file. You can give it a local path, or you can give it like an HDFS if you're on Hadoop location or an S3 location. There's a whole bunch of different ways that you can import data. So I've imported 2 things. One, a file, like basically a data frame that I call train, one called test. And this is what I was talking about before, where X and Y are like the names of the columns rather than the actual data itself. So I'm saying let X be all of the column names for train. So something else you'll notice here is like we basically try to, as much as possible, replicate the pandas syntax. So I would say we're basically a subset of pandas syntax. So you know, things that you would expect would work should work, and if they don't, you know, you could create a ticket. But basically, we don't want you to have to learn like a whole new way to interact with H2O frames. So in Python, we replicate the pandas interface, and in R, we replicate just the regular R data frame data interface. And I think we're actually going to add the data table. Do you guys use? Well, there's only like 2 R people here, but if you like data table, we're going to add that. Because the guy who writes data table works at H2O. So, so let me just paste this in, then I'll show you like, okay, so this is a pretty boring like data set. I probably should have explained what it is. It's like a Higgs boson data set. So there's like, I don't know, 28 features that just represent weird like physics stuff. I don't know. So, and then you're figuring it's a binary response. So whether or not like something with the Higgs boson, I should probably like have a better explanation for this data set. But it's on the, if you type in UCI ML Higgs, it's this Higgs data set. So this is a classification problem to distinguish between a signal process which produces Higgs bosons and a background process which does not. Anyway, that's what we're predicting. And then one other thing that we're going to do first is we are going to encode the outcome in as a, like in R, we call this a factor. In Python, typically call it like an, I don't know, categorical, I guess, or in Java, you call it an enum. It just means like, for classification, basically, in binary classification, you can either use like 0 and 1 and represent the 2 classes that way, but in H2O, the way that we tell the algorithm what to do is we encode the outcome in the proper format. So in scikit-learn, for example, they'll have 2 different methods. Like one would be random forest regression, and one would be random forest classification, or if it's classification or classifier or whatever. But we just have like a random forest. And so the way that you tell it what you want it to do is if it's encoded as a factor, it will do classification. If it's numeric, it will do regression. And typically, it'll already be a factor if you have like yes or no or some string representing your two levels. But this is an example to sort of like demonstrate this explicitly because we have zeros and ones, so H2O would guess that that would just be numeric if you don't tell it otherwise. So this is just, once you do this once or twice, you'll remember about it, but it's one thing that I forgot to do like a bunch of times. I ended up with a regression model, and I'm like, why do I have a regression? I was trying to do classifications because I forgot to do this step to encode the outcome. And remember, we did part of the stacking algorithm is doing cross-validation, so we're just going to tell it how many folds do we want. And this is kind of like a tuning parameter for stacking. So the more folds, obviously it will take more time, but it'll get better performance. So I don't know, I just use 5. You could use 10, or 2 would be the minimum you could use, and that would, if you have like really big data, you could probably just do that. So, all right, I'm going to try to hurry up because I'm running out of time. All right, so this is basically just training 2 models. I'm training a GBM with like these particular, parameters, and then a random forest, and then I'm just going to ensemble the 2 of them together. So let's do that. So we're first going to build the GBM, and then it builds the random forest. Which takes a little bit longer. And once that's done, then we'll just take those 2 models as a list, and then we pass that on to the Stacked Ensemble estimator. Okay, random forest. Just wait for that. Okay, and now we're going to okay, so see, that was very, very quick because all we have to do is the meta learning step. So now what we'll do is we will evaluate the ensemble performance on the test set. So all H2O models, the way that you can get model performance on the test set is just the name of the model or the name of the object. Like if I did my _RF dot model performance, it would give you the model performance for that, and then you pass on your test set. And the reason it's called model performance is because it actually calculates a whole bunch of different performance metrics. So, so you run this once, and then if you wanted like the ABC, you could grab that out of there, or for accuracy, you could grab that, or you can just have them all. So they just get calculated all at once. So the reason that I'm doing this is, okay, so I'm going to evaluate how well did the ensemble do on the test set, and then I'm going to compare it to the baseline. So this is, to motivate, like, why do we do this? Okay, so of the 2 baselines that we had, the best AUC that we got was 0.7698, and the ensemble was 0.7735. So really that is a bigger number than that, so that's good. So this is just an example of, one thing. We're getting better performance. I should say that, like, you're not guaranteed to get better performance. Like, you should always check, because you might have done something weird or put in, like, bad models and they just like destroyed your ensemble. It is possible to get worse performance with the ensemble. It's pretty rare, but it's always good to check. And also it's like, I always like to just know what all my models are doing anyway. So this is just, if you wanted to just generate predictions with the ensemble, all the models in H2O, you just say model name dot predict, and then you give it a test set or whatever, and then you can actually get the predicted values if that's what you want. Usually what I want to do is just, I always care about the performance, so I just grab the performance, which will do this sort of under the hood, and then also get the performance. So, all right, I'm kind of running out of time, but I'll just copy all this code and paste it, and we'll just run it together at once, and then compare it there. Well, maybe I should just, let me just show you the grid search because you probably haven't seen that before. So I did show it on the slides, but basically, here's the different parameters that we're going to iterate over. So learn rate, max depth, sample rate, and column sample rate. And here I'm going to say, you know, randomly sample from this grid, and then only give me, like, stop after you get 3 models. So I could say stop after you get, you know, 20 models or whatever. Just for time purposes, I'm just going to use 3 models. And then we will train the grid. So this will build the whole grid, all 3 models. You know, typically you might like want 100 models or something like that, but let's just make it easy. So now we're just going to pass. So right now, actually, you have to pass the model ID rather than the model object. We're going to change that so that you can pass both. But that's just a side note. So everything in H2O has like a key, like an ID. So every data frame, every model, and that's how we keep track of everything in like the distributed server, H2O cluster. Okay, so then we built that. And now we'll just do the thing where we compare the ensemble performance to the other thing. Okay, so this time we had 0.7481 was our base. And I'm looking at all the base learners and just showing you which is the best one. And then the ensemble is 0.7529. So again, we're doing better. And on Kaggle, that'd be like 1,000,000 spots on the leaderboard. So it may not seem impressive, but it just depends on what world you're living in. Okay, so let me just go back to my slides really quickly. And let me just mention a few things. So how many of you have heard of or like XGBoost? That's also like super popular on Kaggle. So in the next release of H2O, we will actually have XGBoost inside of H2O. So that's kind of a big deal for me because that means I can make stacks or ensembles of H2O models and XGBoost models together and like just totally win Kaggle. And like I'm not very like good at Kaggle, so I think maybe this will really help me out. So in like an ensemble of a Kaggle team, I'm like not that great at feature engineering, but I'm like good at the ensemble part. So if anyone wants to like, team up sometime and help me with the feature engineering, then I can do the ensembling and I can teach you all about that. Okay, so this is good for Kagglers. So this is like almost, I mean, it's ready. We just haven't released it yet. And then if you're an R user, well, nobody is, but 2 people are. There's these other packages that you can also ensemble H2O with like basically anything else. Superlearner, Subsymbol, MLR, and Caret. But that's more for like small data. They're not scalable. Even though H2O is scalable, the way that these work is they like, I guess the H2O part would be fast, but they work with data in memory in R, so it can't really scale. And then I'll just mention this idea of AutoML because it's another project that I'm working on, and Lauren, who's sitting over there, is working on, and some other people at H2O is sort of like basically a function where you take away all the parameters and you just say like, get me like a really good model, and I don't want to like do any work. So that's like the idea with automatic machine learning is just you let the algorithm go off and like do all like typical like stuff that a data scientist would do, like big grid search and like, you know, feature generation and like all this business that, you know, data scientists typically do. And so that's coming out soon. It's not out yet, but I was told a week. I don't know if I believe that, but like it'll probably be out in a month. Maybe 3 weeks, maybe 2 weeks, I don't know. But it might be out like in the next month. So, and anyway, Stacked Ensemble is a big part of that because the goal with AutoML is basically just to get the best model. You don't care like what's happening under the hood. And then this is just some links for all of like H2O stuff. All of the meetup materials, including this slide deck, is in this repo. So all of our meetups, just make a folder and put all of our slides and code if we have code. Yeah, so those are some good links. And then this is how you can find me if you need to get a hold of me. And anyway, thank you. Okay, I didn't go too far for my time. All right, I'm going to pull up Joe's presentation. Okay. What am I doing here? All right.
Question for us? Thank you very much.
Yeah. I forgot to ask if you have any questions, so maybe I should ask that. Yeah.
Do you ever, in your projects, find yourself needing to go in and figure out which learners perform better on which segments of your data? Or is that typically not a step you?
Yeah, so that's kind of like you could. So the package that I pointed to that's called Subsemble is a package that does that. So essentially, like this will be added to H2O where you can use different like data sets basically as in the ensemble. Right now, actually you could probably do this if you used a weight column and just said zeros for all the rows that you don't want to use. But ideally, yeah, you can chop up your data into pieces and train models on different pieces of the data and then see like which ones, typically that's what happens is that certain algorithms are good on certain subsets of the data and other ones are better on other subsets. So it's kind of what stacking is replicating on its own, but you can actually train the base models on different subsets of learners as well. But yeah, yeah.
So you said you get L predictions from L different models.
Yeah.
Like how do you arrive at the final prediction? You said it's not an average. What technique you use there?
So that's just the meta learner. So the meta learner just learns how to best predict the outcome from each of the learners. And so so essentially, like if your meta learner is just a linear model, it would just be like weights, like a weighted combination of, and that's actually what we use typically is, and actually in the stacked ensemble method, it's hard coded to a GLM right now with non-negative weights. In the H2O ensemble, you can specify different meta learners, but on one of my slides, I said support for custom meta learners coming soon. So this was just released like, I don't know, a couple weeks ago. So we'll add the ability for you to say, I want a deep neural net or something like that. Typically, like GLM works well, deep neural nets can work well, but like tree-based methods don't work that well for meta learners. Yeah. Anyone else? Yeah.
Are there any kind of tools that are like cookbooks, so to speak, with like different kinds of prompts and what kind of structures or what kind of learners or what kind of learners might be like useful for any kind of
I don't know of, like, I know some things in my head, but but I don't know that I've run into any like sort of write-up of that. That's probably something that like I should do, or some Kagler, like really good Kagler should probably do. I mean, it's typically like whatever algorithms work well on your data set. Like if you have like a very, let's say, skinny, dense data set, like maybe a tree-based method would be very good for that. And well, maybe not very good, but maybe like compared to like a very sparse, like wide data set where trees don't work as well. So you would just like look at your data and say, okay, what methods do I think would probably work well? I'm just going to shove them all in the ensemble, and then the ensemble basically decides, or it learns what's working well and what's not. So you can put in stuff that's, you can put in bad learners, but you don't want to put in like really, really bad learners. So sometimes I put in GLMs, and it like kind of messes things up because GLMs are like usually way worse than everything else. So yeah, I would say keep your eye out for like really poor performing base learners, and you can just pluck them out and like get rid of them and then retrain.
So you would try to kind of train, like, not exactly like one each learner individually, see what they're going
I would probably do it like the opposite way. I would just like I would use the Ensemble software to train or to basically as a utility just to evaluate them all at once, and then maybe I would pluck some out if they thought they were really doing damage. But in general, even if some learners are like not as good, if they add diversity to the ensemble, they can still it's still sometimes better when they're in versus out, except for GLMs, which are usually hurting people. Yeah.
Do you regularize your meta learner?
Yeah. Yeah. Usually. I mean, you don't have to, but right now, like the GLM in H2O is by default, it uses regularization, so that's what we use. Yeah.
How do I perform stacking with different deep neural networks? For example, right now, my colleague is running a cafe neural net model.
Mm-hmm.
I'm working on inception model.
Okay.
As a problem. Can I do stacking with different types of different models?
So that's a good question to segue into our next talk. So Joe is going to talk about this project called Deep Water, which is like an H2O wrapper around TensorFlow, Caffe, and MXNet. And I have yet to actually try to do that, but because the code is like finally done and this code is finally done, I just need to bring them together. But essentially, like right now, you could use the multi-layer perceptron that's in the regular H2O package to do different deep neural nets. But the idea with Deep Water is that I haven't tried it, but it should work. And if it doesn't, like, we'll fix it. But you should be able to do stacked ensembles with all these other packages. So if you have a TensorFlow and a Caffe model and whatever, it should work. I don't know if it works yet, but we'll find out soon, I guess. Anyway, I will let Joe come up and start his talk.
Good evening. Thanks for staying. So I want to talk to you about a new project at H2O for Deep Water. So I'm Joe Fai. So I've been Joe Fai for a long time. So then I went to England. 2 weeks later, some people start calling me Joe. So that's why I'm Joe from now. So this is a new project that we did to integrate some of the open source deep learning tools. Okay. So before I start, I want to talk about myself. So I was a civil engineer. So I didn't start with the traditional computer science background. But at some point, I discovered H2O. So that's 2014. That was also the time that I first saw Erin talking about her subsample package. And then that is a event that I didn't foresee that will have a huge impact on my life. So I actually learned more about machine learning and all the things about machine data science because of H2O. And the moral of the story is that if H2O helped me to become a data scientist, it will be useful, it will be beneficial for you too to learn about H2O and see how it can apply to your project. So after that, I became a data scientist at Virgin Media. It's a telecom in UK. And then I worked remotely for Domino Data Labs, which is a couple of blocks away from here. Before I joined H2O last year this time. So to give you another picture of where I came from, so you can see this is the latest metric content for data science platform. So we can see that I was here, Domino's, and now we're at H2O. Okay, that's enough for marketing. So let's back to the agenda. So thanks, Erin, to talk about the company. So we don't have to go through the same thing again. But I want to go through some of the bits in the machine learning platform of H2O and how it relates to deep learning tools, TensorFlow, MXNet, Caffe, and H2O, the classic H2O deep learning. And what's the motivation of this Deep Water project and what are the benefits for our users, for H2O users, and how you can use it with different interface with Python, R, and web interface, and what are the learning resource for deep water. So hopefully I will get you just enough information to get you started. So after this talk, you can go back and try deep water. Okay, a bit about H2O. So we talk through that. Let's go through that platform again. So I want to mention that is a machine learning platform, not just about deep learning. So I don't want you to go home and think about H2O as just a deep learning platform. It's the whole machine learning platform, which we have different algorithms. So we have supervised and unsupervised algorithms. Deep learning is one of the algorithms that we have in H2O. We also have gradient boosting machines, random forest, K-mean, PCA algorithm in it. And I want to focus on the interface to H2O because for myself, I was a civil engineer. I didn't know a bit about Java. So for me, it's easier for me to use the R or Python interface to use H2O without learning the Java backend. So what the user can expect from H2O is that they can use either the web interface as shown here. You can choose to just use the mouse, click and drag to build different models in H2O. So we don't have to actually use programming language to use H2O. This is just an example of how you can do a simple random forest model in H2O. Of course, if you want to use programming language like R or Python, you can always do that. So this is an example of how to use H2O with R. Okay, so that is a quick overview of the H2O machine learning platform. We have different APIs to interact with H2O Java. So what does it mean that we have? We also have the documentations for different interface. So if you want to look for more information, this is the URL that you want to go to. So it's docs.h2o.ai. Okay, so that brings us to the next topic, which is the deep learning tools, the open source deep learning tools. We want to talk about TensorFlow, MXNet, Caffe, and H2O. So how many of you have heard about TensorFlow? It's good. MXNet, Caffe? Okay, cool. So I want to go through each of them quickly and show you some use case. So the first one, TensorFlow from Google, is hugely popular, and then you can do all the fancy things with it. For example, you can, because it's popular, you can expect more and more people want to use it with different languages. So you have different TensorFlow wrappers for different languages. So H2O Deep Water is one of the wrappers. And this is one of the use cases I really like it. So there's a farming family in Japan. So the farmer's son used H2O or used TensorFlow to help his parents to save time on sorting cucumbers. So what it is to frame the whole problem with the image. So it's like a classification problem with line classes. So the top one here, 2L here, is the best one with the highest price, and then the back one here with the lowest price. So we want to frame it as a machine learning problem using TensorFlow. And actually, there's a video link. If you go get this line, you can go to the video. And it's quite cool. He actually created a machine, the whole process like a factory. So put it in the cucumber there. You can see, you take some pictures of it, and it calculates a score of the cucumber. So that is a score to sort different cucumbers. So I think the highest score is the best class, and the lowest score is the lower class. And then we put it into different boxes. So that this guy used TensorFlow to do this thing, of course with other kind of equipment in one place, and I think it's really good. And I couldn't show the GIF here, but it's like this guy using TensorFlow to learn how to drive Mario Kart. So if you get to the link and see the actual video of it, that's cool. So what I want to say is that there are many use cases because TensorFlow is open source. It's open source, and people can try it without paying anything. So they come up with all the different ideas of how to use deep learning for their own projects, for fun or for business. The next thing, MXNet, is also really popular deep learning library. So they have different interface. They have Julia, they have Python interface, and we really like it because it's flexible to configure different kind of networks. And you can see that has been chosen by Amazon as the deep framework. So this is another cool library to look at. And then we have Café. I didn't use it personally, but I heard good things about it because there's a model zoo online, so you can expect to see a lot of models from different people. They use different data sets to train their own deep learning model. And I can put it there, and then people can just download it and use the model. And that's quite cool about sharing your deep learning model. And then we have H2O Deep Learning. We call it the classic H2O Deep Learning. So it's one of the algorithms you can see at the bottom. And this is also cool because people have been using H2O Deep Learning to win cargo. So they use it because I personally like to use H2O Deep Learning first because it's easier to learn, easier to use with our API. And that's how I started to use H2O first. And then this is a survey last year by Katie Nuggets. We know that H2O were actually quite popular as TensorFlow at that point in time. I think TensorFlow is going a lot stronger than right now, but still we figure out that TensorFlow and H2O are really widely used for deep learning. So what's the point of talking about all these tools together? The main message here is that with these open source tools, TensorFlow, MXNet, Café, and H2O, classic H2O deep learning, we kind of give the power of deep learning to everyone, to all the people. And with the H2O platform, the user-friendly platform, we can put all this together as a package, as a single platform, to enable every user, not just the business user, not just the data scientist, but for many people to use deep learning with a user-friendly platform. And this is the whole idea of the Deep Water projects, to bring all these two together into a single platform. And with that, we can leverage all the goodies from different algorithms, different tools. So we can use a GPU backend from MXNet, from Café, from TensorFlow with the H2O platform. And that enables the users to have more choices of algorithm, more choices of the problems that they can solve. Now they can do a lot more with the image, video, speech, text, and a lot more things that you can expect from different deep learning tools. And this is quite important for us because we want to expand our user base to tackle more and more problems. We don't just want to do the classic H2O, which is focused on tabular data. And now with this Café, MXNet, and TensorFlow in there, we are more flexible than ever before. But we don't want the user to learn about different syntax, different architecture of the tools. So we want to package them on the H2O platform. So what the users will see is the same Python and the web interface flow. It interacts with the H2O Java, the engine JVM. And then what we figure out in Deep Water is we have the seamless interaction between the H2O Java with the TensorFlow, MXNet, Café, and C++. But the user doesn't need to. The user don't have to learn about how they work together. All they want to see is this interface here with the new function called Deep Water. And we also have the connection between GPU and CPU. So if you have a good infrastructure with all the cluster with CPU, you can use a lot of CPU for deep learning with H2O as well. So we're kind of providing a unified interface for the user to use different deep learning tools in one single platform. So what the user see on the interface, there is the new option here, Deep Water. So it's just like one of the new algorithms that you can find in H2O. They don't need to go through all the installation of MXNet, TensorFlow, and Café. They just need this version of H2O, and they will have all the benefits from different tools. And what it means for the more advanced user is that they can have more choices of network architecture for deep learning. So we have the DNet, IXNet, VGNet, all the more complex infrastructure that you can easily use in H2O Deep Water. But you can imagine that if you want to learn how to configure each of those networks in different tools. You have to learn the syntax and how to transform the data into the right format. But now we have H2O Deep Water. You actually don't have to steep learning curve. Just put all the data like what you would do for the normal H2O, but then you have the power to do more things. For example, in the flow interface, you can just go to the network option here in Deep Water, and then you can choose one of the more advanced, more complex architecture. And then if you want to switch from TensorFlow to MXNet, all you need to do is to change the backend here from TensorFlow to other MXNet cafe. So the user can just switch from different tools and different architecture with a few clicks. The same applies to Python interface and R interface. So this is showing the Python interface for Deep Water, and you can see that the two options to switch from different tools and architecture is similar to the flow. So for that here, you can change from net to IXNet, MachineNet, other network type. And if you want to change from TensorFlow to MXNet, again, you just change the backend argument to the other tools. So that means you can have a single interface, and you can switch from different tools and architecture quickly in one single platform. And that's powerful when you want to stack different models together. So like the question that gentleman asked, so about how to stack TensorFlow with MXNet and with other H2O model. We are trying to do that with H2O Deep Water. That gives you the total flexibility to just stack each model with different configuration together really, really quickly. So you don't have to go through from the ETL for TensorFlow for MXNet. You don't need to change anything. Just a same single platform for all this. Is there a question there?
Yeah. So I'm using a lot of GPU acceleration, right?
Yeah.
And when you are toggling between these different models, how gracefully does it work with the variables? And like with this, who put our DNNs?
Yeah. So we have the option to choose whether you want to use the GPU backend or the CPU. So when it's GPU, is using a CUDA. So actually, it's the Java of H2O talking to GPU. So we figured it out in Deep Water, and that's one of the hardest bits for the team to figure out how to do it, to use CUDA with Java.
So as of now, you have not run a lot of validation when you were switching between like TensorFlow and MXNet with the CUDA on one. So as of now, you have not used the GPU clusters enough when you were switching.
I'm not sure if I understand your question.
So if you're into the GPU cluster, right?
Yeah.
And when you were choosing the different options,
yes.
have you validated with the CUDA drivers? Do they remain stable?
You mean stable in terms of how to use the MXNet with the GPU?
When you were switching.
Yeah, that's what we've been doing the testing for. So we make sure that each time we switch from TensorFlow to MXNet, it's trying to giving you the right number by utilizing the data in H2O, going through the correct algorithm in TensorFlow, talking to the GPU, and returning back the result to H2O Java. So we're trying to do all the tests to validate that. So that's what we've been doing for Deep Water, to make sure that we get the right answer from different algorithms and tools. Okay. Okay, so that is back to another stacking questions before. So this is our simple example that I did a few weeks ago. But I was using the H2O Ensemble package rather than the new Stacked Ensemble. But it's like a proof of concept. It works. So in here I create a deep water model here. The first one maybe you can see it on a slide later. So that is a deep water using the MXNet for regression problem. And then the next two model is the classic H2O GBM and the H2O random forest. So I can use H2O Ensemble package to stack them together, and that gives us a lot more flexibility of combining TensorFlow, MXNet, and Caffe model in the future. Of course, we'll move on from this H2O Ensemble to the new Stacked Ensemble at some point, but this in trying to prove the concept that we can actually stack deep water model with other classic H2O models. So again, I want to remind you that if you want to find out more information about deep water or all things about H2O in general, so docs.h2o.ai is a website you want to go to. And in here, in this section here, in this column here, you can see the deep water documentations. If you want to try it, I would suggest you go to API, so we can spin up an instance on Amazon and try out deep water without building the whole thing from scratch. You can still build it from scratch if you follow the instruction on GitHub. So we use there's a deep water repository on GitHub, so you can follow the instruction and build it on your own. And then you can find more examples. So we have a lot of examples here, including the one that I saw before. So this is all the Jupyter notebooks for deep water. So you can see how we configure the different architecture in different examples, from the simple one to the more complex one. So I want to show you one of the simple one here. Is the cat and dog mouse demo. So we try to classify from pictures. So like this picture here. So you can see they are like just JPEG of different cats, dogs, and mouse. So they're unstructured. They have different size. So we couldn't do this with the classic H2O before because we have to use a tabular data with the classic H2O deep learning. But now with the TensorFlow, Everstat, and Caffe, we have more flexibility in terms of the input data. So all you need to do is to create another CSV file like here. So you need to identify the right path, the final path, the full path of the JPEG file, and then give you the second column, which is the label. So these are all text, but you can expect you can have dogs and mouse in this CSV. So this is the input for deep water if you want to change on the raw image. So what you get here is, I'll show you the Python interface. Again, you want to start H2O with the import H2O here. So we initiate a cluster of H2O, which is JVM, and then we import the estimator for deep water. So that's the API for deep water in Python. And then we pointed to the path, to the CSV that I showed you before with the full JPEG path and the label in the second column. That's how we link it to the H2O. Now I want to show you the basic usage of deep water. So this is the basic network that you can build in deep water. So I'm showing this before. So this you have to define the network that you want to use. This time I want to use the net for that structure. I want to use TensorFlow here. So that is the basic usage of deep water. And then you choose the mono train with the x equals 0 is the first column, which is all the file paths of the JPEG, and 1 is the second column, which is the label of cat, dog, and mouse. And that will give you the basic model of deep water trained with TensorFlow on GPU. So if you have the monitor of GPU, then you will see that it's using the GPU for training. So you can give it a go, and we try it on our AMI. You can see that you can use this example and give it a go on this notebook, and you can see that usage on GPU. Some users, they want to use a more complex network. They want to have a custom network, right? So they want to use a different usage here. Let me go through here. Okay. Oh, this is the end of the training process. Here you can see that is the conclusion matrix of cat, dog, and mouse based on that simple net model. So next thing we want to do for one user is that we want to configure a more complex neural network with TensorFlow in this case. So this is how you can do it. So this is more syntax for TensorFlow. You don't have to actually look at the details. All I want to show is that after the configuration of your custom neural network, you want to save it as a meta file. So this is the file that we want to save on. So we save this structure as a file, and then we use this file to tell deep water that we want to build this kind of neural network. So this is the function to create the actual meta file. So once you have that file, you can just point it to network definition file here. And that is the way to utilize your own custom neural network with deep water. So the interface is basically the same. The only additional bit is to point it to the custom network. And then you can see the same process building model, and then you can see the conclusion matrix for that neural network. So that is the basic and the more advanced usage of deep water. Of course, you can expect more or less the same if you want to switch it to a different architecture or different MXNet or Café. So let me quickly conclude it. So with deep water, we can combine H2O with TensorFlow, MXNet, and Café. This is like a really powerful combination of some of the widely used open source deep learning tools. And you can also expect all the user friendliness from H2O platform. So all the things that you usually use with H2O, you can do the same with deep water with the same interface for TensorFlow, MXNet, Café. This unified interface will allow the user to build, to test, or to just create lots of different models quickly, and you can stack them together using the Stacked Ensemble or H2O Ensemble. And everything is open source, 100% open source, and the party will get bigger. So, for example, we have the XGBoost implementation. That's not part of deep water, but you can see that we can implement more and more open source tool in the H2O. Then you can user will have more and more choices. I want to thank my colleague here. They are the main contributor to deep water. So I'm more like a user, so I don't actually contribute to the deep water, but I like to use this as a new toy for me in the H2O stack. And then if you want to ask any question generally for H2O or deep water, you can go to community.h2o.ai, so you can search and ask questions there. That's another website I want you to remember. And finally, I want to thank the organizer, the artist. Thank you for this one. It's great. And if you want to get all the information, this is again the meetup link, so you can see today's presentation and all the previous presentation, all the talks that we gave in the past. And if you want to go and look at deep water repository, you can see all the code, all the instruction to build deep water from scratch, or all the Jupyter notebooks from there. If you want to contact me for more information, my email is quite easy to remember, the joe@h2o.ai. Lastly, I want to show just this article from TechCrunch. So we got mentioned by them saying that we're trying to put the deep learning power into the hands of business users. So I hope that after this talk you will have some time to try out deep water. And if you want to have some feedback on how we want to give us some feedback on how we can improve this for your projects, just feel free to get us to send us email, or just go to community.h2o.ai and send us some feedback. So that's all. Any question? Yes, please.
My question is about the pre-trained model. So
Yeah.
for deep learning, sometimes
Yeah.
it takes a long time to train a model from 101. So that's about the pre-trained model. So for deep water, how can we import the pre-trained model?
Yeah, we're actually working on that. So we don't have that in the AMI that you see on that. So we're trying to include that functionality so people can have the model from Café model from the model shoe, put it into deep water, and do the rest from that. So we're trying to do that now, but it's not in that AMI with this. It will be at some point this year. Yes.
In the cat dog mouse example that you showed,
Yeah.
I think I saw that the images had all different sizes.
Yes.
But then, like in the model syntax, you specify the expected image size.
Yes, that's a way to unify the input of unstructured data. So we're saying that we want to resize the image to 28 pixels by 28 pixels. So even though they come with different sizes, some rectangle, some square, we use that to define the actual input size of each image, so they are unified when they go into TensorFlow.
So like deep water handles.
Yeah, you can define that. So this is how it allows user to just focus on the problem, so they don't have to do the resize themselves. They don't have to do it before deep water. They just need to specify the range of that the size. So 28 by 28 is the size that you want to put in. So if your memory card, your graphic card has more memory, you can make it bigger. But usually, it depends on how much memory you can use for this deep water project. So imagine if you make it bigger, you will consume more graphical memory. Okay. Yes.
So I'm a student here. Just out of curiosity, have you noticed like any one of the backends being faster than the others or something along those lines?
Do I have to answer this? So I think that in my opinion, we have more mature implementation of MXNet. That's my answer.
Okay.
But I'm not trying to give side to any of the tools. But we are trying to include more and more into H2O. So the reason is that some of the algorithms are good for some data sets, and we never know that before you try it. So if by implementing different algorithms, different tools in one single platform, you can just test, experiment different algorithms in one single platform. And that is quite useful for Kaggle, for most practical machine learning process to test, to experiment, and find out the best.
Okay, cool.
Any more questions? Yes.
You're not specifying a batch size here. Is that independently, or is that a?
There's an option.
Part of a distributed data structure that you've got set up on the training.
We do have the batch size parameters in there, but I'm not using that here. But let me see if I can show you the default value. Okay, I think from my memory is about 64. The batch size. I think that's if you go through the flow interface or the help document, you can see the default value of batch size, and you can set that in Deep Water. So that again is the same thing that you would expect from different MXNet and TensorFlow. Any more questions?
Can you build text summarization models?
We're working on that. So we are getting more and more formats. So we support text. We're trying to support more format like time series and other formats. But we don't have enough use case yet. So that's what I need to work on more in the coming months to create more and more use case on different problems. So not just for image, not just for simple table data. So we will create more and more use case so people can look at this use case and see how they can apply it to their own problem. It will come at some point.
Thank you.
Thank you.
Thanks so much, everyone, for coming. We still have some more pizza and drinks. You guys want to stick around? I know it's late, so thank you for staying this late with us. If you have any questions about Metis, please let me know. And of course, if you have any H2O questions, people from H2O around. Thank you.
Joe, I might be going to the ODSC masterclass.
Oh, yeah.
I saw you're doing a couple lectures. Can you give me an example